In 2006, an unusual step was taken in the history of astronomy. A planet was officially stripped of its planetary status. This decision was based on a clear definition, yet it also raised serious questions. But does this definition truly describe a world like Pluto in an accurate way? Since that day, the decision has continued to be debated within the scientific community. So was this really the most scientifically sound approach? In this video, we examine the scientific basis of the 2006 decision and why it remains controversial. By 1930, the solar system appeared orderly and complete on paper. Uranus and Neptune had been discovered, their orbits had been calculated, and the overall structure of the system seemed logically consistent. Small rocky planets on the inside, giant gas planets on the outside. However, small yet consistent deviations, measured in Neptune's orbit, suggested to some astronomers that an undiscovered mass might exist at the outer edge of the system. Pluto was the object sought in pursuit of this idea. When Clyde Tombaugh, through patient and methodical observations at Lowell Observatory, identified a faint point of light that shifted position relative to background stars by comparing the same regions of the sky over days and weeks, it cannot be said that anyone fully understood what had been found. What mattered at the time was this: something had been discovered, and this something was a body orbiting the Sun. Pluto's acceptance as a planet was shaped by the astronomical mindset of its discovery era. At the time, the definition of a planet did not rely on detailed orbital or dynamical criteria as it does today. Large bodies orbiting the Sun and distinct from known planets were naturally classified as planets. Pluto's mass was not precisely known, its diameter was estimated, nothing was known about its surface, and even the existence of an atmosphere was uncertain, yet none of this was considered problematic. There was simply no alternative classification. However, Pluto's orbit is markedly different when compared to those of other planets in the solar system. Most planets orbit the Sun in nearly circular, low-inclination planes, whereas Pluto's orbit is far more elliptical and significantly inclined. This causes Pluto to periodically move inside Neptune's orbital distance. These characteristics fundamentally distinguish Pluto from the rest of the system in a dynamical sense. Pluto's distance from the Sun is directly reflected in its orbital period. One Plutonian year is approximately 248 Earth years. As a result, since its discovery in 1930, Pluto has not yet completed a full orbit around the Sun. Its return to its discovery position is expected to occur around the year 2178. This long orbital period further emphasizes Pluto's distinct position within the solar system's timescales. By the late 20th century, advances in telescope technology and the introduction of CCD cameras enabled far more sensitive sky surveys. This technological leap revealed that the region beyond Neptune was far more populated than previously assumed. Initial discoveries were sparse, but soon a clear pattern emerged. These objects were small, icy, dark, and orbited the Sun at great distances. They appeared to be concentrated within the same region of space. Today, we call this region the Kuiper Belt. It contains thousands of small, frozen bodies and can be thought of as a kind of residual debris field left over from planet formation. And Pluto was located at the heart of this structure. While all other planets reside in a relatively cleared region between the Sun and Neptune, Pluto exists directly within the Kuiper Belt. In fact, we can now state this clearly. Pluto is not merely a Kuiper Belt object. Pluto is the first Kuiper Belt object ever discovered by humanity. This is ironic, because when Pluto was discovered, astronomers were not yet fully aware of the Kuiper Belt's existence. The belt was first proposed theoretically by Gerard Kuiper in 1951, but the first observational discovery did not occur until August 30, 1992, by David Jewett and Jane Law, 62 years after Pluto. Since then, more than 2,000 Kuiper Belt objects have been identified, some of which are comparable to Pluto in size and mass. This directly raised one of the central issues affecting Pluto's classification within the solar system. By the late 1990s, astronomers faced an uncomfortable question. If Pluto is a planet, why are these other large Kuiper Belt objects not planets? And if they are planets, how many planets do we have? As a result, the International Astronomical Union officially revised the definition of a planet in 2006. According to this definition, a celestial body must satisfy 3 criteria to be considered a planet. First, it must orbit the Sun. Second, it must be massive enough for its own gravity to shape it into an approximately spherical form. Third, it must have cleared its orbital neighborhood of other large bodies. Pluto satisfies the first 2 criteria. However, the third criterion, clearing its orbit, became the decisive factor. Clearing the orbit refers to a planet becoming gravitationally dominant in its orbital zone, either by accreting nearby bodies or ejecting them from the region. In other words, the planet controls the local dynamical environment. Pluto, however, shares its orbital region with many similarly sized Kuiper Belt objects and does not exert such dominance. For this reason, the 2006 decision reclassified Pluto, ending its approximately 76-year status as a planet and placing it in a new category, dwarf planet. This definition was not unanimously accepted. Some astronomers argued that the orbit clearing criterion is fundamentally flawed. The core of this criticism lies in a simple fact: no planet, including Earth, has completely cleared its orbit. Earth shares its orbital region with tens of thousands of near-Earth asteroids, and the same is true for Jupiter and the other planets. As a result, the consistency of the third criterion has been questioned. Alan Stern, principal investigator of the New Horizons mission, described the decision as a bad decision shortly after the vote, arguing that the definition contains internal contradictions. These criticisms show that the Pluto debate is not merely about classification, but about how we define the very concept of a planet. Following the 2006 decision, the Pluto debate continued largely on a conceptual level. However, it did not remain purely theoretical. At the same time, a spacecraft was already on its way to Pluto. The New Horizons mission was planned when Pluto was still considered a planet and launched toward a target now labeled a dwarf planet. Far from diminishing the mission's importance, this context made it even more significant. This was not just a planetary flyby, it was humanity's first direct exploration of the solar system's most poorly understood region. In 2015, as New Horizons approached Pluto, the prevailing expectation among scientists was simple: a cold, geologically dead, largely unchanged ball of ice. But the moment the first high-resolution images arrived, this assumption collapsed. Pluto's surface was not uniform. Instead, it displayed remarkable diversity: smooth, crater-free plains, sharply bounded mountainous regions, complex fracture systems, and a vast, heart-shaped bright feature. This structure, known as Sputnik Punisher, stood as direct evidence that Pluto's surface is not passive. From this point onward, the classification debate shifted. The question was no longer simply, is Pluto a planet, but rather how this complex and dynamic world should be understood within the solar system. Detailed analysis of the images revealed that Pluto's surface does not share a single geological history. Heavily cratered regions exist alongside nearly pristine areas, indicating that different processes shaped the surface at different times. In planetary science, this contrast has a clear meaning: crater-free or sparsely cratered surfaces are young or actively resurfaced. Some regions on Pluto appear to be only a few 100 million years old, a surprisingly recent age on solar system timescales. The most striking example of these young surfaces is Sputnik Punisher, located in the western part of Tambor Regio. This approximately 1,000-kilometer wide plain stands out due to its smoothness and lack of craters. But its importance lies not only in its appearance. Its physical properties point directly to active processes. Sputnik Punisher is covered primarily by frozen nitrogen, methane, and carbon monoxide. At Pluto's extremely low temperatures, these materials do not behave like rigid water ice on Earth. Nitrogen ice becomes viscous, capable of slow flow and deformation, reshaping surface features over long timescales. New Horizons data clearly indicate that such ice flow is occurring. This observation implies an internal energy source. If Pluto's interior were entirely frozen and thermally dead, such large-scale resurfacing would not be possible. This shifted attention to Pluto's internal structure. Sputnik Punisher lies almost exactly along the axis connecting Pluto and its largest moon, Charon, and appears to create a mass anomaly within Pluto's overall structure. Such an anomaly cannot be explained by surface ice accumulation alone. It requires a denser layer beneath. The most compelling explanation is the presence of a subsurface ocean beneath Pluto's thick ice shell. Gravity data, surface morphology, and regional alignment collectively support this hypothesis. This ocean would not consist of pure water but likely a mixture enriched with ammonia and salts, which lower the freezing point and allow liquid to persist at extremely low temperatures. It is important to avoid misunderstanding the terms subsurface ocean. This does not imply an environment similar to Earth's oceans. The key point is that Pluto retains internal energy very slowly, allowing internal complexity to persist over billions of years. This internal structure aligns with observed surface fractures and extensional features, suggesting long-term internal stresses. Pluto thus emerges not merely as a frozen Kuiper Belt object, but as a world with its own internal evolution. Pluto's thin and transient atmosphere further complements this dynamic picture. The atmosphere exchanges material with surface ices, driving seasonal changes and reinforcing Pluto's unexpected activity. New Horizons discoveries do not automatically restore Pluto's planetary status. Planetary classification depends not on how interesting or active an object is, but on the criteria used. Under the 2006 IAU definition, Pluto remains excluded due to its shared orbital zone. However, these observations force a reassessment of the definition itself. Pluto's complexity conflicts with the intuitive simplicity implied by the term dwarf planet. The debate thus shifts from what Pluto is to whether our categories adequately describe nature. A classification is valuable only if it helps us understand reality. If it obscures diversity, it must be questioned. Pluto demonstrates that the outer solar system is far more dynamic than once believed. The Kuiper Belt is not merely a collection of insignificant debris, but a region populated by worlds with complex internal structures and long evolutionary histories. Pluto, as its first discovered member, remains the clearest reminder of this reality. New Horizons flew past Pluto only once and did not enter orbit. Many questions remain unanswered, including a direct confirmation of a subsurface ocean, a long-term monitoring of atmospheric behavior, a detailed understanding of geological mechanisms. These questions can only be addressed by a future mission. Perhaps by the end of this century, we will return to Pluto, with the first spacecraft to revisit this distant world.